Hello everyone and welcome back to our new lecture. This is the second lecture in part 3 of the course. In this lecture we will be talking about two theorems which are very important, and as you know by now that all what we are doing is just using the derivative applications to understand more about our function. The first theorem I want to talk to you about is Rolle's theorem. Rolle's theorem tells you that if you have a function that is continuous on the closed interval, let's check this function. We have this function, it's continuous. Do you see it? It doesn't have any breaks. It's continuous from the beginning of it till the end of it. And it is differentiable on the same interval but opened. So this function is differentiable at the same interval. At any time throughout this function, at any point in this function, it is differentiable, means the right and the left differentiation are the same. And f of a equals f of b, the y value of the first point equals the y value of the last point or the final point, then there will be a point between the interval where the derivative equals 0. So again, if my function is continuous, if my function is differentiable, if it starts and ends by the same y value, then within this function there will be a point like this point where the slope is horizontal or the derivative is equal to 0. Here are different examples. Like for example, in here it's differentiable, it's continuous, so I have only one point where the derivative equals 0 or the slope is horizontal. In here I have, it starts from here and ends from there, again starts and ends with the same value, differentiable, continuous, and I have 2 points where the slope is horizontal, C1 and C2. In here I have it down. And I'm not sure if you noticed or not, usually in Rolle's theorem we have an increasing then decreasing function, or a decreasing then increasing function, or both, increasing then decreasing, and here decreasing then increasing. This is usually where you have a horizontal slope. Alright, let's take an example. Verify that the function satisfies the conditions of Rolle's theorem, then find all the numbers that satisfy the theorem. Here is the function, it's a polynomial to second degree, and this is the interval. So we have 3 checks, or we have 3 steps to do. First, I need to check if it is continuous. Well, polynomial functions are continuous on R, and they are usually continuous on their domain, so it is continuous, check. Is it differentiable? Let's differentiate it and see if there's anything not differentiable. So the derivative will be 2x minus 3. So yes, it is differentiable. Third check, let's check the y value of a and the y value of b. So I computed f of 0. I just substituted here x equals 0 and I got a value of 2. And then I'm looking for f of 3. I went to my equation and I substituted x equal 3 and I got 2. So since f of 0 equal f of 3 equal 2, then Rolle's theorem applies, and there exists a point where f dash of x equals 0. In order to find this point, let's actually set the derivative to 0 and solve for x. So I took the derivative from this second step to x minus 3 and I equated to 0 and I solved it and I found x equal 3 over 2. The last check that I need to do is to make sure that 3 over 2 is actually in the given domain. 3 over 2 is in the domain of 0 to 3, so this is the point. Another example, verify that the function satisfies the conditions of Rolle's theorem and find all the number x that satisfy the theorem. Okay, let's revise. I need to check that it is continuous on the closed interval. I need to check that it is differentiable on the open internal. I need to check that f of a, which is the first point in the interval, which is here 1, f of 1 equals f of 5. If all of them apply, then I will find the x. Okay, let's check. First thing, check if function is continuous. Here is my function. To know if it is continuous or not, I'm checking the domain. So the domain is r minus 3, because the domain is r minus the value of x that makes the denominator equal to 0. So x minus 3 equals 0, so x equals 3. So it is r minus 3. So at x equals 3, there is a vertical asymptote. Therefore, it's not continuous. You know that one of the discontinuities to have a vertical asymptote. So it's not continuous at x equals 3. Let's check the domain. X equals 3 is inside the domain. Therefore, Rolle's theorem does not apply and I cannot find this value x. Another example. I have here a polynomial function and he wants me to verify that the function satisfies the conditions of Rolle's theorem on this given interval and then find the values of x. Again, my steps. First thing, check if it is continuous. Polynomial functions are continuous on R. Let's check if it is differentiable. I differentiate it and I found it's again polynomial, so it is differentiable. Let's check the f of a and f of b. F of the first point, which is minus 3 over 2, and f of 3 root 2, same value. Then the theorem applies, and then I will equate the derivative to 0, and I will solve, and I found two values, x equal negative 3, x equal 2. Right now, I need to check that these 2 points are in my interval. Well, x equal negative 3 is not in the interval, so I reject it. But x equal 2 is in my interval, so yes, it is accepted, and this is the point he's looking for. Here come another example. He's giving me my function, and he's asking if the conditions do satisfy Rolle's theorem in the interval, and then find the values x. So I'm doing the same checks. The first check to check if it is continuous. I look at the function. Well, there is a restriction to the domain. Since I have the square root, 4 minus x has to be positive, so it has to be greater than or equal to 0, so x should be less than or equal to 4. So this satisfies the given domain from 0 to 4. Let's check if it is differentiable. So I differentiated and I looked at the differentiated and I found a square root in the denominator. So again, a restriction to the domain. So the domain is from negative infinity to 4. So again, it satisfies the given interval. Because to be differentiable, it has to be to 4 opened. It doesn't need to be closed. So it satisfies. And then I need to check the start point and the end point given in the domain. So I check their values and they are the same. So right now I know that Rolle's theorem is applied. And then I equate the derivative to 0 and I'm trying to find x. So this is the derivative. I equate it to 0 and I found x equal 8 over 3. The final step is to check that this number is in the interval. I go, it's from 0 to 4. So this one applies. So this is the point. Again, another example that tells me to apply Rolle's theorem to this function within the interval from 0 to pi over 2. First, I need to check if it is continuous. So if you just look at the components of the function, which is sine x and cosine x, each one of them is continuous. The sine x function is continuous, the cosine x function is continuous, so this function is also continuous. Are they differentiable? Let's differentiate and see. If I differentiate the function, it will be cosine x minus sine x. Again, both of them is differentiable. Let's check f of a and f of b. So f of 0, starting point of the interval given, equals 1. F of pi over 2, which is the end point of the function, again 1. So therefore, the theorem applies, and there is a point where the derivative is equal 0, and I will equate the derivative to 0 and find it. So I took the derivative, which is cosine x minus sine x equals 0. And I need to solve it like a trigonometric function. So I divided by cosine x, so this became 1 minus tan x equals 0, so tan x equals 1. Again, I need to check my domain. My domain is only in the first quadrant, so the only angle that makes the tan of it equal 1 is pi over 4, and pi over 4 is in the interval, so this is the point. The mean value theorem is another theorem that is very important. The mean value theorem tells you that if your function is continuous on a closed interval a to b, just like the red one drawn in here, and it is differentiable on the open interval of the same 2 points, then there will be a number c in the interval where the slope drawn at c, or the tangent at point c, is going to be equal to the slope of the secant line joining the 2 points a and b. Let's look at the graph. You see the secant line drawn from a to b, it's parallel to the slope drawn at point c. So f dash of c equal f of b minus f of a over b minus a, which is delta y by delta x. In other words, the secant line connecting the starting and ending point of the interval and the tangent line at x equals c are parallel. Parallel means equal. Let's take an example about the mean value theorem. So it's telling you, can the mean value theorem be applied on this function on two different intervals, one from -1 to 1, the other one from 1 to 2? Well, we have steps to check. First, let's check that it's continuous on the closed interval. So to know if it's continuous or not, I need to check the domain. Well, in the domain, I have a restriction that the denominator can never be equal to 0. So the domain is r minus 0. So let's check if 0 is in my domain. Yes, it's in my first domain. Therefore, this first domain does not satisfy the mean value theorem. Let's check the second domain. Well, the second domain does not include the 0, so yes, I can say it's continuous on this domain from 1 to 2. Is it differentiable? Well, let's check. I differentiate it. I find this is my function. Again, it's not differentiable at x equals 0, but x equals 0 is outside the domain of 1 to 2. Therefore, the mean value theorem here can be applied. In here, he didn't ask me about the x values that can be satisfying the mean value theorem. If he asked me about it, I would have found it using the equation, but here he didn't ask. He was just asking if the theorem is applied or not. So here I told him the theorem can be applied on the second interval, which is 1 to 2, but it cannot be applied on the first interval, which is -1 to 1. Another example, verify that the function satisfies the conditions of the mean value theorem. Find the values of x. Here is the function. It's a polynomial function, and this is the interval given. Well, polynomial functions are continuous, polynomial functions are differentiable. And thus the theorem applies, and there is a point, x, where its derivative or its slope is going to be parallel or equal to the slope of the point between a and b. So I did the equation f dash of x equal f of b minus f a over b minus a. I substituted and I found x equal 2. I need to check that this is still in the interval. Yes, so this is the value. Another example, verify if the function satisfies the mean value theorem and find all the values of x. Here's the function, interval from -1 to 3. First step, check if it is continuous. Well, it's continuous except at x equals 3. But 3 is in the interval, so the mean value theorem does not apply. And I do not continue. I just stop in here and I know that it doesn't. Another example, verify that the function satisfies the condition of the mean value theorem. Find all the values of x. Well, this is the function. I know there's a restriction in the domain, so there's points where it will not be continuous, and here's the interval. So my first check, continuous, checking the domain. Well, what's under the square root have to be greater than or equal to 0. So x has to be greater than or equal to 3 over 4. I check my domain. So yes, I am continuous on this domain. Is it differentiable? I differentiated and I looked again at the domain. And again, I'm safe and x is greater than or equal to 3 over 4. So then the theorem applies, and then I find the number by doing the derivative of the function to be equal to f of 3 minus f of 1 over 3 minus 1. And I just did the equation and I found x equals 7 over 4. Again, I need to check my interval and that this point is in the domain given. It's in the domain and that's the point. Another example, a little bit different. He's telling me that the function, a certain function is defined, it's continuous and differentiable. And we know that the derivative of this function ranges from 3 to 4. And we know that f of 0, if I substitute it in the function with 0, it's going to give me 2. What can I know or what can be said about f of 5? Well, let's check. I know the function is defined, continuous, differentiable, then the mean value theorem can be applied. And then I'm going to give the interval I'm interested in. So since it's giving me some information of 0 and is asking about 5, so I made my interval from 0 to 5. And then I applied the equation that f dash of x equal f of b minus f a over b minus a. And I substituted with the given info. For example, I know f of 0 equal 2. And then I'm left with the fact that f dash of x equal f of 5 minus 2 over 5. But I also know that f dash of x is between 3 and 4 from what's given here. So what I'm going to do is I'm going to substitute f dash of x with this formula in here and then solve again to try to understand what's can be said, or what we can know about f of 5. So this is what I did. I put here f of 5 minus 2 over 5, the formula that I reached from the derivative, and I put the 3 and the 4 which are given. Alright, I just need f of 5. So what can I do? I will multiply all of them by 5. I will get rid from the 5 in here, and then I will add plus 2 to all of the sides, and then I'll be left by f of 5 is greater than or equal 17, but less than 22. This is what can be said about f of 5 using the mean value theorem. This is the end of this lecture, and I hope that it was easy and understandable. Let's all hope that everyone is safe and we are taking the right precautions. And until I see you in next lecture. Thank you.